Okay, so what do we have for questions here?
Let's look at the back, honestly.
Sure. Do you have any specifically in mind, or you can make something up that's always dangerous? Oh, by the way, folks, let me also remind you, the last time I checked, I think 2 out of the 5 in here have like done a course evaluation. Make sure you do that. Always. So we might as well, let's just at least start, and if this doesn't save you, then that's fine, we can do something else. Let's start with the 2 that we had last year. So I gave you a couple last year. I said, first sketch the graph of the function x to the 5th minus 15x cubed. This must be easy to take a derivative of, otherwise I'll probably get a position. Right. And what's the first derivative of this? 5x. While I'm at business, 20x cubed minus 90x. So let me actually, let's make this a little bit easier. Right, this way. Factoring makes it easier. I guess 10x times 2x squared. So when I do my analysis of what the first and the second derivative, I'm going to need to pick out points where the derivative and the second derivative are either 0 or undefined. Now, undefined is off the table here because these are both polynomials. Find everything. So what numbers are important for the first derivative? I agree with that. How about the second derivative? So let's do a couple of sign charts here. So yeah. For the first derivative, 0 minus 3, 3. Okay, you all tell me what happens when I'm to the left of negative 3. Right. Here's a way you can simplify this too. Let me point out that no matter what, this thing is positive, right? And so it's not ever going to interfere with what's going on. So this piece right here, x squared minus 9, is the only thing that controls the sign, right? So when you're in between minus 3 and 3, it should be negative. When you're outside of it, you should be positive. This means y is increasing, decreasing, decreasing, increasing. At these 2 points, what happens at negative 3? Okay, both lines. I agree. It goes up and down, right? And this occurs at negative 3. I don't really care that much. It's minus 60 minus 27. It's 162 or something like that. What happens at zero? This function continues separately. You're not going to get any verticalized. That's one way. For specific functions, yes. I'm not going to say universally yes, because, for example, that function is undefined as zero, but does not have a vertical asymptote. You know what this looks like? It looks like 1 if x is not 0, and does not exist if x equals. So this is what this function is like. No vertical asymptotes on that, so you have to be careful. Right? Now, if you have a rational function and you get a 0 at the bottom, that's very likely it will be a vertical asymptote. But see here, you get 0 at the top and the bottom. L'Hopital's will tell you the limit is 1. Actually, go to the big one. Just cancel the x and the limit. What happens here on this one? 0. Okay, that's a great observation. Y prime is 0, so should it have a horizontal tangent line, but it is neither a max nor a min, right? It's not an extreme. And 0, 0. What happens at 3? Okay, so let's look at the second derivative. See what we can get from this. Again, we have 3 points to consider. So let's see. This one's a little tougher to check, but we can persevere. What happens if you're to the left side of minus right of the derivative? Something like negative million. Positive. So the whole thing is negative. What happens if you're in between here and here? Something like, for example, -1. Negative, negative, positive. What happens if you're between here and here? Something like +1. Positive, negative, negative. So every one of these changes. When x is huge, this is positive. So this becomes concave up, or concave up, concave down, concave up. These are all what we call points of inflection. That is, points on the curve, the concave changes positive and negative. I think we're in decent shape to be able to try to draw this. So let's give that a shot here. Okay, so I'm going to get some points to get my bearings to start things off. I know the point 0, 0 is on the curve. I know the point -3, 162 is on the curve. So let's say that's that. Oh, positive. Positive. Here, every point here, -3, +3, -162. So let's see what happens. Notice that when you go up to -3, this first local max, it's always sad, but the concavity doesn't change until after you pass this. So it's always sad and it increases until you get this. Now, on its trip down here, the concavities begins sad, but then it changes to happy at some. And we also observe that it's got a zero slope tangent, so it's like happy, look like that. And I'm gonna fudge this, it's sort of hard to tell, and it's 3 over radical, negative 3 over radical. But now on the other side, it comes out, it is still decreasing, and it changes to sad. And then eventually it changes back to happy. It's that minimum. So make a change right here. And this gives everything we need, right? Increase, decrease, increase. And the concavity is sad, happy, sad. Everybody okay with that? Okay, so let's try another one. Let's try the other one. It says sketch the graph of g of x is x cubed over x squared minus 1, which equals, okay, so I wrote it as things. This one, next one first. X cubed over x squared minus 1. And I rewrote it this way for you, and that helps. Plus x over x. And I already can tell something about this one. Think about that while I talk to you. The first derivative is x fourth minus x squared. X squared minus x squared. And 2x cubed plus 6x. X squared minus plus 6x. Okay. Okay. Any observations we can make? Forget the derivatives. What observations? Just write up there. Ooh, very good. That's best observation. This is actually what happens to this thing right here when x is humongous. This is almost zero, right? And so this means on a big scale, if you stood back and looked at it, they're on scale of 1 million, 2 million, 600,000. That's good. Like this, it'll do some weirdo stuff here in the middle. But on the big scale of things, this function starts to look like y equals x. Somehow. Right? There's a little goofing around here in the middle, but on the big scale, it's going to look just like y equals x, because that goes away as x is very large. So that's something to keep in mind. And we'll get more specific on that later. What else do we have? It's got a slant asymptote, but it's also got something else. It's actually got 2 vertical numbers, right? Because when x gets very, very close to either 1 or negative 1, this top is getting close to 1 or negative 1, and the bottom is getting very close to 0. So this is becoming huge. I expect this to be a vertical asymptote. So here's kind of my little primitive thing. 1 and -1, there's some kind of vertical asymptote behavior. Maybe it's like this, maybe it's like this, maybe it's like this and this. And then on the big picture, it's gonna look like equals X. Okay, so I've got that in mind. So I expect X equal ±1 be vertical asymptotes. Now, what numbers do we need to worry about here? Do our sign chart, what numbers do we need to concern ourselves with? ±1 for sure, right? I mean, those are not really critical numbers because you can't plug them into the original function. Be a critical number, you also have to plug it into the original function, but that we have to put them on our sign chart because the sign of derivative changes there. There's also some others, you guys see what we do. Zero's one of them. There's 2 more. I know what the other 2 numbers we have to consider. Because after all, this top thing here is x squared times x squared minus. The x squared bit gives you the 0, and this gives you the +1. In the same spirit of this, let's see how this factors that might help us. This is 2x times x squared plus 3, I guess. So what numbers do we need to consider here? Well, ±1 again for certain, right? What about what's on top? Only 0, right? Because there's no solution to this part. So we gotta break there. Right there, you can't x squared plus 3 equals 0. No real solution. So let's go through this business with the sign charts. We've got to mark up this one for sure. Zero, we got 1, got square root of 3, and we go on the side, -1, minus square root of 3, and this is G prime, G. And G prime is x squared minus 3 over x squared minus 1 squared. Now that seems like quite a mouthful, but guess what? This piece, right here, is always positive. X squared is always positive, x squared minus 1 plus x squared is always positive. So they do not affect the sign of the outcome. So the sign of G prime is determined completely by this term right here. And so in between radical 3 and negative radical 3 should be negative. Positive. Doesn't that beat plugging in something for everything? You just notice that this piece is all positive. We take it out. So this function increases, decreases, 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 increases. What happens here? Say local max, isn't it? Minus square root of 3, and whatever you get when you put that in here, which I guess is going to be 2 in the bottom and minus 3 right at the top. So it's minus 3 half right at the 3, I guess. So, but it doesn't matter. Okay, what happens here? Particle asymptote. Particle asymptote. What happens here? It's very similar to the last. 0, 0, not critical. It is critical. Not extreme. And 0 slope 10. And what happens here should be a local minimum. And it's point radical 3, 3 half. While we're at it, let's do the second derivative. Of course, we're going to have less points here. 0 minus 1, 1. Notice that this is 2x times x squared plus 3 over x squared minus 1 cubed. And notice this time, this piece is always positive. The other can be positive or negative, but this piece is always positive. So what happens to this thing when x is, say, to the left of -1? It's negative, because you have a negative here and you have a positive. What if you're in between -1 and 0? So you want negative a half. Negative, negative. How about plus 1/2? Positive negative. So it's negative. And if x is humongous, then the positive and positive. So I get the G is concave down, concave up, concave down, concave up. How many points of deflection? Move on. 0 is the only true point of deflection because it's the only one that's a point on the curve. -1, 1, a vertical asymptote. There is no point on the curve. So it is true that concavity changes as you pass through those numbers. It's not a point of inflection because there is no point. So let's try to draw this. I'm going to write this observation we all made earlier. Y equals x is a slant asymptote. That helps us. So let me try to draw this. Y equals x. X equals 1. So I'm not going to be that great on the scale here, but you know what? Since let's actually do this in between the vertical asymptotes first, right? Because you've got kind of 3 places that it is. It's here on the left side of this, it's in between the asymptotes, and it's on the right side, the right asymptote. We'll see what it looks like in between the asymptotes. So we're in between -1 and 1. So this is easy. It's always decreasing, always going down. And it's concave up, so it's happy until it hits the origin. And then it's sad. So I think I can draw it. So it's decreasing all the way down. So it goes off of this asymptote and down this one. It's happy, has a 0 slope tangent here, and it becomes sad after. So probably something like this. That's what it should look like. Right up there. Now, let's do it, because it's easier to work. Positive numbers. Let's figure out what this looks like on the right, with x equals 1. And the first question I might ask you is, y equals x is a slant asymptote. Does the function, is it above the asymptote? Is it below the asymptote? Or does it maybe go back and forth, wiggle toward it? Sometimes you get functions that do like a big wave and smaller waves as they get closer to the asymptote. You can touch an asymptote. So which is? I agree. How do you know? Seems like it should be that way, right? But there's clues. There's several clues. Here's one of them. When I draw this, it's going to be decreasing. So it's going to be coming off this, right? Like this. And it's going to hit it's going to hit this local min at radical 3 and like maybe right here. And notice also that my function is always smiling. Everybody agree with that? It's always smiling. So happy hits its min. Now, if it's going to continue to increase and smile, it needs to come in above that asymptote, right? Because if it ever passes through the asymptote, it continues to increase and smile, we're going to have a problem there, right? There's also another thing, and this is even more. Look at the way I rewrote this function. What this says is my function that I'm trying to draw is the function y equals x plus this and this. And I don't know much, but I do know that this mess is positive, right? Because x is bigger than 1. So you got a positive numerator, and since x is bigger than 1, you've got a positive denominator. So what I'm drawing, my g should be actually the function plus a little bit. So it's always going to be on top of it. Like this. And you get a mirror image down. What happens here? You're always concave down. You increase to the local max right there, and then you decrease, and you're always in that. So that's what that's. Any questions? Is everything kind of want to see there, everybody? Yeah, and notice also, this equation also tells you below the asymptote when you're to the left of -1, because this is x plus a little adjustment. Now, if x is less than -1, that's negative and that's positive. So it's x minus some stuff. So whatever it is should be hanging below the line of x. Okay. Other questions?
So we need to.
Sure. This sum is example, right?
It's a Riemann sum.
Okay. In this problem, we use the definition of the definite integral to find the interval from 0 to 3, 6x squared minus 2x. So this is basically our target. 6x squared minus 2x. it's important to know, one of the reasons it's important to know this, is that any interval is a limit of sums is not just from theory, because if you remember that a limit of sums becomes an interval, it will make lots and lots of the application of 1080 when you do it a lot easier. Right? This animal is sums. So let's go through the way that we kind of built this magical mystery to it. It says find the Riemann sum that expresses the approximation of this desired interval using n evenly spaced intervals and choosing the right endpoint. Okay. So just so I can remember, so here's the interval from 0 to 3, correct? And I break this up into n evenly spaced intervals. So the width of each one of these, how wide is each one of these? The length of the total interval, which is 3,500. Okay. It's one of the things I asked. Oh, I gotta find the whole Riemann sum. N evenly spaced. Okay, I need to know where the right endpoint is. Split it in their homework. Yeah, very good. That's right. That's actually K1. So is everybody with him on that? Right? The right endpoint of the kth interval is move over from 0 to k times by 3 over n. Right? That's essentially that. Everybody come over? So f of x star is f of k 3 over n. And in our case, this is 6 k times 3 over n squared minus 2 k. So we're just about at the cusp of being able to do Riemann sum. Riemann sum is sum x star delta xk. So for our case, we know k1 n. F of x k star is this mess. So it's 6 k 3 over n squared minus 2 k all times delta xk, delta x, which in this case is and there. That's 3 months. Okay, now in part B, it says, okay, take this and take an appropriate limit. Limit what? As it goes to infinity. Yes, we want to find out what happens to this as it goes to infinity, but we need to clean it up first. It's kind of good. So to be able to effectively do this, this is the part where I do a little bit heavy lifting. Some algebra here. So let's rewrite our Riemann sum. write this as sum cosine from 6 times minus 54 k squared over n squared. This is going to be 6k or 6 over n. Okay. All times sum 162 into squared minus 18 squared. And that's just multiplying the side. So I get, so this is kind of an improved way of writing off my sum. Well, this is 162 over 8 cubed sum minus 18 squared. I think it doesn't need to really write the Riemann sum in perhaps a better form. What might I do now? That's right. You might look at the board or say, hey, Jim, we're going to learn this up here. This, anybody remember what this one was? What happens when you have 1 plus 2 plus 3 all the way up to n? This one is, how about this one? So, I'm going to take what I've got there and like this sum. So this is what I'll read my sum is going to be 162 over n cubed. That's n plus 1, 2n plus 1 over 6 minus 18 n squared. N now interval 0 3 6 x squared minus 2x x limit is equals to infinity. This thing that I've created. And if y'all remember, I taught you to do this fast. What's the limit of these? That's right. The biggest power been on the bottom is 3. Agreed? biggest power of on top is also, this is kind of a spin-off of the one column. So it should be the coefficient of the n cubed term up here, which is 162, and the coefficient of the n cubed term. Great. How about this one right here? This one would be infinity. Right, right. So for dramatic purposes, like 1802, yeah. So this turns out to be 54 minus 9. Everybody follow what we did there? And of course, the last part says verify this, so 3 points, right? Verify this by using fundamental theorem of calculus. What do we get? Antiderivative of this is 2x cubed. Antiderivative of 2x is x squared. But I put in a 3, I get 2 times 3 squared minus 9 is 54 minus 9 is 45. So looks like very high degree of probability that this is correct. This also, the short problem also shows you the power of the fundamental theorem of calculus brought into our lives, because even this problem, which is one of the very simplest problems that you can do by doing the boxes, because you have these formulas and you work the limit in a fairly straightforward, still made it a lot easier by this. And when you try to integrate things like sine and cosine, x to the x log x plus 1, then you sort of go on and be doing boxes then. Okay, questions? Okay, other questions?
Summer's final.
Yes, so this was last. 2023. Which one did you say 2e? Okay, that's the limit as x goes to infinity. 1 plus 3 over x, the 2x power. Okay, so how are we going to go about this? What's the first thing to do when faced with any limit problem like this? Try to plug in, of course, well, in this case, kind of see what happens as it goes to infinity. So we've got a variable base and variable exponent there. What's happening to the base as x goes to infinity? It's going to 1 plus 0, right? And of course, the exponent itself is going to infinity, right? So this is one of those 1 to the infinity, right? So how do we do this? big thing that helps you make diagnosis. This is variable base and variable response, right? This is kind of a problematic thing to get rid of. It's going to be a variable base, variable exponent, and throw a log in, right? We're gonna do the same thing here. Well, I agree, that's the same thing as the exponential part into each other. But which is that. Now, what's the strategy in this? So the whole point is that this allowed me to pull down that 2x out of the exponent. And so now I've got to figure out e to the 2x log 1 plus 3x is exponential. What's a good next step here? Okay, let's see where the exponent goes. The whole idea is this is e to the something, and the exponentials can do things. Just see where this exponent's going, and that's going to tell you everything you need to know. So let's take a little side here. Limit as x goes to infinity of 2x log 1 plus 3 over x. Again, I should be a bonehead to plug in. What do I get? Where's the 2x piece go? Where's this log piece go? Log 1, which is 0. So this is an infinity 0, which is a L'Hopital rule. But L'Hopital rule was designed for fractions. So what do we do? We get out a pair of pliers and make it a fraction, right? We can certainly do that. And we log 1 plus 3 over x over 1 over x. Now it's a fraction. And again, if you see what happens as x goes to infinity, you get log 1 on the top, it becomes log 1 to 0, and you 0 on the bottom. So this is perfectly reasonable for L'Hopital. So let's do the L'Hopital rule here. Infinity. The derivative of 1 over x is minus 1 over x squared. This is 2 times derivative log blob is 1 over blob times the derivative of 3 over x is minus 3 over x. And just to be clear, this is multiplied. Okay. Notice that the minuses can cancel and the x squareds can cancel. And this leaves me with the limit as x goes to infinity. Well, that's down to just 0.01. So it's just 2 times 1 over 1 plus 3 over x times 3. All that. What is that limit? That is correct. This is 2. This thing's going to 1 because 3 over x is going to 0. So 2 times 1 is 3 is 6. So what's the answer to the original problem? There you go. 6. So the answer to the original problem is 6 pounds. method. Suppose I give you function X, function now. Let's say usually method for X. Let's take first approximation. By the way, I am talking real sure of myself. I said find the root. How many roots are there in this? In fact, you'd be kind of silly in real life to use it because there's only one. It doesn't work this. The root of this function. We have f of x 0. Find what value of x satisfies is just take the fifth power of this and get x equals 0. There's only one root. So I know the root well because this illustrates something interesting. It also shows we figure out what the formula is. F Newton's method, the n plus 1 approximation. I remember what it is. The function of the derivative within x being plugged in. So for our function here, f of x is 1/5. So f prime of x, I'm going to need this one. What's that prime of x? Okay, you all take a minute. We can have a race if you like and see what if you started at 0 1, see what x1 is. Yeah, yeah. That's terrible. X1. X0 is 1. So this is 1 minus, what's f of 0? What happened? What's f prime? 1/5 of 1 to the last 4. 1 to the last 4. This is 1. So a fifth. This should be 1 minus 5, negative 4. What's the next one? This would be x1 is negative 4 minus, it should be f of negative 4. So that's going to be if I put a negative 4, take the fifth root of it, it will be negative fifth root 4. And then f prime of this is going to be 1/5 4 minus 4 fifths. You might say, why is it not minus 4 minus 4? It is, but 4 is an even power, so it's through that sign. So this is in the subject there. Plus, those two minuses cancel. This is 4 fifths, 4 to 1/5. I'm going to multiply this by 4 to 4 fifths, top to bottom. So what did I do? I got rid of that sign and I brought that 4 fifths up. So this is negative 4 plus, that's going to be 4 to 5 fifths. 4 times 5 is 20. So I get 16. Right, okay with that? Okay. Question 1, following up. Somebody explain to me. Well, just given these first two approximations. Is business method going to work here? No, it's what explain why our situation is worse than we started. Yeah, there's only one root, it's 0, and you're getting further away from it. Right, so here's what this function looks like. Y equals x to the 5th looks very much like y looks, even it's more exaggerated. Now, we've all got to run one way. Y equals x. I'm sorry, y equals x. Probably not that great of a scale. Here's one. There's only one root there at 0. You got a first approximation here. Boom. Notice it's not 4 times as much, but it's further away than it was here. Right? So this is the root here, it's now bigger. Now what happens? It's further away than you started. So the function is actually pushing you away from the root. See, this process continues. Because what's happening up here is the tangent lines get flatter, so it projects you further on the opposite axis. Newton's method will not work, right? And the problem is, it's the curve of the function, the concavity is what is messing up. Any questions? So if you know the Newton's method formula, that's okay. I'm not going to ask you to do a lot of hardcore computation. I just want you to know how Newton's method works, right? It works on finding the x-intercept, the slope, of the tangent line, and the direction of the six.
We do, not sure if we do this. We do number 5.
Let's choose example.
Last year's.
Let's choose five. Find the volume of the largest cylinder that will fit inside a cone of base radius R and height H. Okay, this time what we have a cone. We have this cone. Base radius R and this is height H. And inside this cone, I want to put a cylinder. And of course, you should probably have asked me a question about this question because, oh, no, I take that back. I didn't do that right. And what we're trying to do is find the largest cylinder with respect to volume. Notice I can make my cylinder very short and fat, and I can make it very tall and skinny, depending on the size coming. And it seems sort of intuitive to me that somewhere in the middle, there will be the largest cylinder that you put in there. And where that middle occurs should depend on the ratio of R to H. Yes. Okay. Calculus is easy. Hard part's get this set up. So how will we get this set up? Okay, so what we're trying to do, that's a good thing. You know, if nothing else, label this. Does this cylinder have the same radius as the cone? Probably not. So let's call this little r. And let's call this some other letter. We'll call it L. Height. The volume of my cylinder inside there. What is the volume of that given the length? Everybody agree with that? This is what we want to maximize. But what problem would we have? How would we have this problem? Too freaking in there, but I've got a little R, I've got an L, gotta get rid of some. Now, this is very good for addition. However, it's not completely serving my purpose. Don't be afraid to draw another picture. I want to get down to brass tacks. In fact, what I'm going to do is I'm I'm just gonna draw a picture of the cross section, half the cross section. So here is home. It's got radius R. And here's where my cylinder lies. It's got a little R, of course, also down here as well, but. And where's L? Well. I guess this one right here. Oh, this helps me quite a bit. What do you think? Yes, I'm thinking similar lines. Would everybody agree? This triangle I've shaded here is similar to the whole shebang. So if I were to do this. You fill in the rest of this. Oh, very good. So little side is the big side, as little length is the big length. Well, I know what big length is. It's H, right? It's the whole shebang. What is this? Well, you know, it's H anyway. Well, like, is this plus this? And the okay, this is purely a matter of comfort. If you want to solve this for L, solve it for R. Better choice. I think L is a better choice, right? Because if I solve it for R, actually it's easier to solve it for R immediately, but then I'm gonna have to square that out. Yeah, right? If I solve it for H, it might go a little bit better for me. So H over R times little r is equal to H minus L. So L is equal to H minus H over R. So this allows me to get a new improved formula for the volume of that cylinder. A volume is now pi r squared times L, which is H minus H over R. That might be convenient for some ways, and I also write this pi H r squared. And then pi minus pi H over capital R. But is everyone is? What should we do now? Yeah, let's find out what the playground is before we jump on the grid. How small could R be? I agree. I mean, it would be stupid, right? It would be like just a vertical stick sticking to the middle of that cone at the top. But there's nothing that stops us from doing it. No dividing by zero. How big could R be? Big R. Oh, and I'm digging on this. I'm glad that I took the time out to do this because I've got a continuous function on a closed interval. So I'm gonna have to do after I take the room some plugins and stuff. That's good. B prime, remember my variable is little r, so this is two pi r two pi h r two minus three pi h over r. Now that I'm only going to, yeah, so, let me pull some stuff out of this. This will actually factor, because I've got a factor of R here. I noticed that I can pull out pi h. I'll just pull out pi h r. That leaves me two pi h r. That leaves me three r. Three r over count. I know it's an alphabet soup of letters there. But really, I've only got one variable. And that is rule. Somebody give me a credit. That's the interval, and we're going to be testing it anyway. So that one's too big. What's the other one you get? Right, and I prefer it off this way, because what this tells me when I write it this way is I'm just two-thirds of the way over the radius. So I know it's in my playground, right, because it's two-thirds of the way to the. So let's plug stuff in and see. The zero, when I plug in r equals 0, I get 0. When I plug in r, when I plug in capital R, little r, I'm going to h minus h equals 0. And of course, this makes all the sense in the world, because this one right here is a cylinder with radius 0, and this is a cylinder with height 0. So they have that 0 volume. And finally, if I plug in third R, I'm not too happy about it, but I'll do it anyway. This is pi times 2/3 R squared times h minus 2/3 minus 2/3 of h. 2/3 R and this cancels the R. So this is what 4 7 It's interesting because the volume of the entire cone is 1/3 r squared, which is 9/27. So basically, this occupies, the largest cylinder occupies like 4 nights. So let's. Okay. place down here is minutes. Then depending on what the height is, a critical number would be max volume. So 2/3 of the way. There's only dependence on the radius, it's 2/3 of the way over, no matter what, going really tall or really short. Okay, questions? You mean like the number, right? So,
My problem is, I can get the equation where it's like, UV minus,
so you're talking specifically about you want integration on parts. Is that right? Okay.
so when it comes to like mixing numbers in there, that's where I'm struggling.
Well, suppose that we do this, so. Any ideas on parts? So we'll see. So what's the okay. So this be 1/3. It's here. Cosine of 2x. Value of 0.9 minus the end of 0.5 of minus 2/3. So. So this point is it's worse because what did we start out with? We started off with a trig function times what? X squared. Now what do we have? Trig function times. That does not look like the right direction. You keep doing this process, next time you do trig function next to 4, next to 5. So what does that cost? This is why I usually say I take my DV part to be the biggest piece that I can pretty much integrate in my head. So let's try this. Now what do you want to do? And once I do that, of course, this determines what I have to have here, right? Because these two parts, and go back and make the original. It's a good gut check if you set that up. If these two don't put back together, then you've done something. Derivative of this. What's the antiderivative of this? It's like sine 2x, right? But I need a 1/2 to adjust that to. Basically, this is the easiest kind of substitution. Everybody follow what we did there? So now what do we? Well, this becomes 1/2 x squared sine 2x pi over 0 minus the integral from 0 to pi of this cross. And this cross thing is going to be x sine 2x. But now I can wait for the end of the, I'm going to go ahead and evaluate. We'll see. Right. What happens when I plug in pi here? Plug in. It's 0. Sine 2 pi is 0. That's when I plug in 0 here. 0. So you get 0 minus 0. It's gone. So this is the easier interval. I can get sine minus x sine 2x. Now, let's do parts again. What should be the? I'm gonna wait to see your comments. Your choice is perfectly fine. I'm gonna do this. Why did I put minus with that? Right, because the antiderivative will be cosine, and this is just x. So when I put this back together, I get that. So let's. So du is equal to dx. And b is equal to 1/2 cosine. This 1/2 x cosine 2x. And then it's going to be minus the cross. How do I say? 1/2 x cosine 2x. The antiderivative of cosine 2x is sine 2x 2, so it's going to be minus 1/4 sine 2x. But here you can sort of bench it, so for sine 2x, cosine 2x, and 2 outside. So when I plug in pi here, I get 1/2 pi cosine 2 pi minus 1/4 sine 2 pi 0 minus, put it 0, and 0 minus 0. So I get 1/2 pi. Lots of stuff dropped out. Very good. So just remember, I mean, in parts, the numbers, if that's what you were talking about, what the limits of integration are easy, because they don't change. Use substitutions, you're actually changing variables, so you have to change the numbers. You don't change the variable in parts, it's a rewrite. So how about this one? jump out at me. You're right, that's what you would do. There's a couple things that don't look quite right. If you assign what's to you, one, so many ways. And like I said, any of these kinds of true identities, multiplying, whatever, you just need to know they're there. I will give them to you free of charge. All right? That's pretty right. I see that. This is like the two signs. Those signs now get the two signs divided. And now, this thing is begging to have uniform sign X. Right? Because this piece is going to be this piece right here is going to be, and everything else is in terms of signs. This is good. This becomes the integral of 2u5 square root of u squared plus 1 . What else? You know, I'm not done with this. So I need to, well, yeah, but again, I'm not, this is not a finished product. What else do I need to do? What should be bottom? Sign 0, which is here. Power, sign the power 4. Right. No, it's here. 4 radical. Now, we can have a discussion about what to do next. So now we just rewrite this 0, 1, right, 2, 2, 5, square, 1 pound. What now? So this is exactly the kind of thing that I was talking about today, where I have not solved my problem yet, but I've rewritten, right? I've done one substitution. It takes something that looked pretty horrible and made it look at least a little bit better. But we still have to get out of this. Let's try another substitution. Yes. It's a great suggestion. So if we go this route, DZ is going to be 2u. So UD is going to be 1/2. See, so if I look at this here, now this is accounted for. 1/2 You see? So I've got that. And this bit right here. The 1/2 power. Or I'm sorry, not 1/2, 0. But I'm still I gotta get everything worked out. What about this? I've got 4 powers of u unaccounted for. Also, know u squared is c minus 1, so u to the 4 c. So this is so the substitution is going to work. So what am I going to get? Well, I figured it all out. This is going to 2 c minus 1 squared. We can see 1/2. 1/2 PC. And what else do I have to do? Gotta get new limits. What's my new bottom limit? B1. Plug in u equals 0. In the old days, u was 0. In the new days, it's 1. What about my top limit? One and a half. 1 plus 1/2, which is those very conveniently these two cancel. This I'm going to this out. This is c squared over minus 2c 1. Now, almost got what's the general strategy? Right. This is nothing to do. Multiply the student disintegrate is about this. So this is going to be see the 5/2 minus 2 c to the 3/2 1. And this is obnoxious, but at least I can do it. This is 2/7 c 7 minus minus 4/5 c to the 5/2 plus 2/3 c to the 3. Right. This 3/2. Oops. This becomes 2/7. It's 3/2 to the 7/2 minus 4/5. 3/2 5/2 plus 2/3 3/2 3/2 minus. When I put in 1, I get 2/7 minus 4/5 plus 2/3. By the way, a word to the wise, this answer is fine. Do not waste your precious best time. So we went through 2 substitutions, get from this awful thing over to here, and had to change our limits both times. 0 to the power 4, final. That Kathy, you look for? Okay, other questions? Yesterday?
Yeah.
Um, well, I'll make sure I've got the right one. Do you mean the quiz we took on the last day of class?
Yes.
Okay. Oh, the E to the X, E to the E to the X. I'll do it fast. But you the E to the E to the E to the X. What's the derivative of this? First thing I come to is E to the block, which is times the derivative of what's inside. And what's inside is this mess. What's the derivative of E to the block? Times the derivative of what's inside this, and what's the derivative of E to the X? There is no U. This whole thing is du. The antiderivative of U plus C, which is E to the. So it's actually E. Yes. In fact, if you had used a substitution, you would have noticed that its derivative is this. And so there you go. Now, if you didn't see it, what's one thing that you could try? That's maybe not, I mean, this is like, this is shoving the whole subway footlong into your mouth at once, right? How might you take a smaller bite instead of, you know, doing that? Okay, so let's see what happens with that. So. So maybe this is a little bit hard to digest, you know, when you first look at it, so let's try it. Small steps. So let's see what this is. This bit right here is du, right? And this bit right here is e to the u, and this is e to the e to the u. Do I agree with that? So if you do this, this becomes integral of e to the u, e. See what I got, because this, the e to the x dx is absorbed as du. But always remember, it's sometimes a good point to take care of your du first. Here we have. And this is e to the u, and this is e to the e. Do it again. So now, this is now DC, and this is DC. Okay with that? Now you can just write it down. So it's the antiderivative of C. Let's take it back. What was C? It was E. And what was U? U, it was EDX. Okay, other questions? How you feel about the testimony? Fairly confident? Cool. So can you tell me a problem that you want to do? Linearization can encompass a whole kind of thing, like error estimate. Okay, so for example, what's the nearest number to 150? That you know will know where 144. So we want to know. Now, this is where we know already. Yeah. So I will do this from two perspectives. I'll do this once from linearization, or I'll do a tangent. So one, this tangent line, LX, and the linearization is just the tangent. We use take process here. f of x is x to the 1/2, and f prime of x is 1/2 x to the minus 1. So L of x and A is 144. So f of A is 12, and then prime of A. When I plug in 144, this I get 124. Let's see right here. So L of x is f of A, which is 12, plus 124 times x times. And there you go. That's what you, so f of 150, which is square root of 150, should be approximately equal to L of 150, which is 12 plus 124 times 150 minus 150. So you plug in 150 just like it's the square root of 150. 6/24 is 1/4, so I get 49. So about 12.5. Okay, you can also do this from the point of differentials. You know that F 144 is 12. And F 150 is F of 144 plus delta y. And what I'm going to do is I'm going to approximate delta y with dy, which is F prime of x. So usage, which in our case is 1/2 of x to the minus 1. Now here, our x is 144, so that's where we know the value is. And my dx is 6. Because 6 is how much I have to change 144 to get 150. So this is going to be 1/2 and 12, 6. So my change in y should be about so f of 50 would be approximately f 144 plus dy, which is 12 plus. So notice I get the same. This is basically essentially doing the same thing. My estimate too big, too small. So the square root function is thoroughly, that's what I get when I take this part of the parabola y equals a squared, and I rotate it around the line y equals y equals x. So it's going to be 2 bigger to this one. What I'm doing here is I'm using a tangent line to approximate this. Given the way this curve is shaped, any tangent line in our vicinity is going to lie above the curve because the curve is actually not that. So therefore, I expect my estimate to actually be a little bit too big. Richard, is that what you were looking for then? Okay. Others? Like, 2 out of 5, so still got 3 of you got to do it. The reward is everybody gets an extra 100 on their quizzes, factored in. Other questions?